Hi, I'm Alex Tong, and today I will be presenting our work on data-driven learning of geometric scattering networks. Today, we'll focus on the field of geometric deep learning, and the main goal of this field is to translate the success of deep learning on Euclidean domains to non-Euclidean domains. Neural networks have generally found the greatest success on domains with many features, but where the features are related in some way, such as occurs in images and natural language. However, they have had much less success on tabular data, where there is very little inherent structure between features. Graphs relate nodes using edges, which creates some structure that we can use to improve our models. So geometric deep learning is mainly concerned with these graph structures, which is an interesting data model in a number of domains, such as citation networks, where nodes are papers or authors, and edges are citations. Social networks, where people may be connected to other people or posts, or molecular graphs, where graphs represent the 3D structure between atoms or molecules in chemicals or proteins. One of the earliest deep learning models that took graph structured input was the graph convolutional network. In this architecture, each layer is broken down into 3 steps. An aggregation step, where features are aggregated from nodes' immediate neighbors, a standard linear network, which operates on each node, and a pointwise nonlinearity. This type of structure is surprisingly expressive and takes into account our inductive bias that nodes close together in the graph are related. In this architecture, each layer aggregates information from a node's immediate neighbors. To get information from further nodes, layers must be stacked on each other. Each additional layer increases the receptive field of a node by 1. This makes sense in relation to standard convolutional networks, where the common wisdom is that each additional layer can aggregate higher and higher level features, which may be useful for whole graph prediction and regression tasks. However, stacking layers like this presents some issues that have been studied in other works. Oversmoothing is a phenomenon observed in a number of graph convolutional networks or other neural networks, where the features become more and more similar between nodes as depth increases. This limits the depth of useful networks. The second problem is called underreaching. Because of the network structure, the depth of the network is tied to the distance that features can be aggregated. So if you have a very long skinny graph, you may need a very deep network to aggregate features from the whole graph. This runs into the oversmoothing problem. And we will propose a way to extend the range without the problem of oversmoothing by using a scattering priors through an architecture based on the geometric scattering framework. First, a bit about standard Euclidean scattering on images. The low-level filters of a convolutional neural network are surprisingly interpretable and stable between datasets. The top picture shows these first layer features extracted by AlexNet. These features are thought to detect edges and textures. However, it is difficult to understand and analyze these filters as they are learned from large and complex network. This is where scattering comes in. Scattering is easy to analyze theoretically and produces similar filters to what a convolutional network might, as shown in the bottom figure. So recent work has generalized these Euclidean scattering networks to the geometric domain. Here we perform scattering on a graph with a signal vector, which gives us a vector representation of that signal that has provable stability and equivariance guarantees. Recent work has shown that by using a support vector machine on the scattering embeddings, this gives good results on standard graph classification tasks, particularly on social network datasets. However, this is a fixed transformation that is designed not to be trainable using gradient descent, and therefore is not adaptable to different types of graphs easily. So we must set the parameters manually for each data set. To get a sense of what these diffusion wavelets look like, here are some diffusion wavelets on a graph with points sampled uniformly from the unit square. Diffusion wavelets on graphs can be defined similarly to wavelets in the Euclidean domain using the diffusion operator, which we call P, especially on this graph, which can be viewed similarly to wavelets in the Euclidean domain, but can be extended to other graph shapes. So here across, we can see longer and longer time diffusions, and down we can see diffusions at different points in the graph. Finally, we can present our learnable scattering architecture. Here we take an adjacency matrix W and a set of signals X, and instead of taking fixed differences of few signals as shown on the left and was done in the past, we learn wavelets that are mixtures of different scales and can adapt to different graph types. The main thing here is to make sure that there are wavelets and differences between successive scales. So to make sure we learn the scales, we perform steps. 4 steps. First, we calculate the scales of diffusion between 0 and 16. Then we learn a mixture of scales for each bump using linear layer and softmax. And then we sort bumps from the lowest to highest scale by their largest weight, largest scale. And then we calculate wavelets using the difference of successive bumps. This ensures that we get actual wavelets and we can assure theoretical properties about them. We showed that by this learning of scales allows us to adapt to different graph types, and particularly it helps on molecule graphs, which have a large diameter relative to their size. We use 3 kinds of networks: legs RBF, which is a learnable scattering network module followed by a radial basis network; legs FCN, which is a learnable scattering module followed by a fully connected network; and legs fixed, which is a architecture where we fix the scales and only train the fully connected network for comparison. So here we can see that legs RBF and legs FCN work particularly well on these top ones, which are biomedical data sets, and they work fairly well on the social network data sets, but really it's the molecule graphs where this really helps to improve things, this learning of scales. So we can also look on molecule graphs, more specifically on regression tasks. So on the Casman QM9 data sets, the task here is given a bunch of molecules, predict some features about the graphs. And so we can see here that it's even more clear how well this learning of features is helpful. So in conclusion, we presented a learnable scattering network which can learn the fusion scales. And so this is more flexible than fixed scattering, but maintains the theoretical guarantees. And it has improved performance by mitigating some of the problems of oversmoothing and underreaching that are present in graph convolutional networks. Thanks for listening. For more detail, see our code in our paper linked here.